So that leads us onto our technology, Automist Smartscan. What we've got is a wall-mounted head. It sits at about light switch height, 1.4 meters off the ground. It's initially triggered by a combination alarm that tells our head to scan back and forth through 180 degrees. We're looking for a dangerous fire, and when we locate it, we are firing a targeted blade of water mist into it to suppress it. And the important point here is that we can tackle dangerous fires with 1/10 of the water of a traditional sprinkler system. So the system draws approximately 5.6 liters of water per minute. That means you don't need a tank, you don't need a water upgrade. You can connect it to your existing water supply. So therefore it's very easy to retrofit. You can see the kind of makeup of the product there on the left. You've got your spray head. We've got it's connected to a pump, which is about the same size as a PC tower, a small PC tower. And in a small flat, it might look something like this. Here we've got 2 pumps under the sink in this case. And the heads, up to 6 heads, can be connected to 1 pump. These are spread around the property to ensure you've got a uniform coverage throughout the space. Now, just to explain how it works, well, these heads are paired to the alarms, alarms which are put throughout the property. In a fire situation, what would happen is you would have the nearest alarm trigger. The heads connected to it would then begin scanning. The data from these heads would be compared, and they would say, okay, one head would say, I've got the best visibility of the fire. The other head would close. That head would activate. And this is a really important point. Because we're only activating one head, we can limit the water requirement to 5.6 liters of water per minute. This is a significant point because when you have a traditional sprinkler system and you're covering a large space, this room, because of something called AMAO, which is the assumed maximum area of operation, if the fire sapped an equal distance between each one of those heads, you have to assume that all 3 of these heads will activate, and therefore you have to provide an adequate flow or water supply so all of those heads can produce the same flow and pressure as was seen when those systems were tested. So that means in a room or an apartment with a large open plan space, the water requirement isn't just the 60 liters of water per minute. It then increases depending on the number of nozzles, and so in this case 180. So this assumed maximum area of operation can mean that the water requirement is very significant in larger buildings. The FIA recently gave some guidance about retrofitting in high-rise buildings, and they said that it was important that designers assume the AMAO is at least 216 square meters. So you can imagine that's quite a significant requirement that is necessary with traditional systems. Okay, so the next part is the detection. On the top right of the screen there, you can see what you would visibly see in a fire, and below is an IR trace that gives you an indication of how our sensor would see a room with a dangerous fire. This is important to note that even if you have obstructions within the room, because the heat is forced out of the fire up vertically and spreads out across the ceiling, it makes it quite easy for our pyrometer to pick out the location. The other thing that we do is utilize the same methodology that rate of rise heat sensors use in order to confirm a fire is there, and they use something, a fire engineering principle called T-squared fire growth curves, where we're looking at the rate of rise which changes depending on the fuel packet, but we're looking for those conditions to say to our head to confirm, yes, there is a fire and I'm going to operate. So this graph here shows the scans from our head as it sweeps through 180 degrees over time, picking up that on this one particular point we've got the temperature rising. We can confirm that there's a fire in that location, and we're gonna activate. The reason we're confident that the system works is because we've done a lot of fire testing. So some of these videos were filmed here in the UK, some of the standard tests that we did. Some were done with our partners out in America. One of the things that we wanted to do was so that we could be confident that the system would perform outside of sort of test conditions, was we set up loads of scenarios looking at the common causes of fire within the home, whether it was bed linen, curtains, concealed fires in a washing machine, just to be absolutely confident that the system is going to perform when it's called upon. A common one that we often get asked about is, well, what if there was a fire directly under the head? We tested to see that it would perform in that case, and this next video is going to show when there's an obstruction in between the fire load and the head. So you can see the shield in between. And what actually ends up happening is, because we're forcing a large amount of water mist in and around the fire, because when the fire essentially breathes, it sucks in oxygen across the floor. The larger the fire gets, the more water mist it draws in towards it to suppress it. So you can see some of the different examples of this. There's numerous videos on our website and YouTube channel. Okay, so the other benefit that we have of being an intelligent and an electronic system is we can build up a library of data. So every fire test that we do, every activation incident that we can get access to, we would download the data, so we get a heat profile in our database. And this is really useful because it means we can optimize when the system activates and ensure that it activates reliably. So if Mr. Smith burns the toast, you have an initial spike of heat and smoke, but the temperatures don't follow those T-squared fire growth curves. The temperature comes down after the event, so our system can determine whether or not it believes it's a dangerous fire or not. And this is something that we are improving all the time. Okay. The other question that we get asked a lot is, well, why do we mount our spray heads lower down? Traditional sprinklers are always mounted on the ceiling. And we do this because we spoke to this man here on the right. His name is Professor Ragnar Vigus, and he was the ex-president of the International Water Mist Association. And he said that the optimal way to use water mist is to use the natural turbulence that the fire produces. So you can see here on this diagram, a fire, as I said before, sucks oxygen in across the floor, pushes out this heat through its center, that then spreads out across the ceiling. So traditional sprinklers, what they do is they use large droplets that have to flow using gravity against this kind of updraft that the fire produces, in order to get the water right into that base, into the center of the fire. The problem with deploying smaller droplets from the ceiling is that these droplets evaporate and turn to steam before they get into the base of the fire. So what you end up doing is first cooling the hot layer on the ceiling before you're able to address the fire. So we mount our heads lower down because we want as much water mist as possible to be sucked into the fire's base to suppress it. Indeed, if you go to Scandinavia and you go to some of their aircraft carriers, they mount their water mist nozzles into the floor. Now that's obviously easy to do because in an aircraft carrier it's going to be open. So we picked the optimum position, we felt, where we can get as much of this water mist entrained into the fire, but at the same time go over obstructions that you might see within the home. This is another video that we did some testing over in Missouri, where we compared the fastest acting residential sprinkler to Automist Smartscan. They're identical fires. We know they're identical because we took thermocouple data alongside this test. The first thing that you will notice is that Automist Smartscan detects and addresses the fire 2 minutes before the residential sprinkler, and what the insurers who were at this test were equally pleased to see with our system, and you can see really illustrates it there. Because of the amount of water we use, we minimize the consequential water damage that occurs as a consequence of active fire suppression.